Hello everybody. In this video we're going to talk about one thing related to the three component diagram or the ternary diagrams, and it is more related to the liquid extraction, which is one of the main focuses of the ternary diagrams or the main uses of ternary diagrams. So I have already discussed the ternary diagrams in details in the liquid extraction videos in the Microsoft Excel series, so you can go and revise them if you need more information. But I will quickly mention what I want to revise here. So this is the three components that we have. This is an isothermal ternary diagram of acetone, chloroform, and water. And as we see, this is the equilibrium curve that we have, which is the raffinate and extract layers like together. So both are like on the same curve. One side is the extract and one side is the raffinate layer. And these lines here that we see between the two sides of the curve are the tie lines, and this tells us what's going to be the compositions of the two layers when they separate spontaneously, if we have a mixture that has a composition in here. And as we see, the tie lines are not parallel, and they have different angles of inclination based on the experimental data. So this is not something that we can predict. And there is a point here that so we can tell that this is one side, which is gonna be, let's say, the extract layer, and this is the raffinate layer. So it's not like symmetrical curve. So the line that or the point that separates the two equilibrium curves is not in the center, so it's somewhere here. And this point is called the plait point, and this is the point of this video, because I have been asked the question about the plait point and how we can determine the plait point. So the plait point is the point here. Can be here, can be anywhere, but we can tell from the tie lines that it is somewhere between these 2 points, because it should be this point is on the extract and this is on raffinate, and the same for the next tie line. So as you come closer to the plait point, you can see that the tie line is getting shorter, and this makes the region where the plait point is lying smaller. So at this plait point, we will have no tie lines. It's gonna be just a point, and this tie line, the plait point, is important for like a very critical reason, because as we said that the tie lines and this ternary diagram, we use it for the sake of doing liquid extraction. So if I have a mixture and I know that I'm gonna be at the plait point composition, then there is no point of what I'm doing, because if I have it here, then the extract and raffinate layer will have the same composition at this point, so no separation is going to take place at this point. So it's important for me, when I mix the solvent with the liquid mixture that I want to extract the solute from, that I know that I am far from the plait point, so that I can achieve something with this separation or with this liquid extraction process. Otherwise, I'm gonna start with what or end up with what I started with, and it's gonna be a useless process. So it's important to determine the plait point, and as I said, it's not something that we can get by calculations, because the tie lines are not easy to predict with the random angles that it's inclined with, or slopes that you have here. So one thing that we can do is to predict, it's not doing calculations or exact calculations, but predict from the shape of the tie lines that I have here how the plait point will or where the plait point will lie. So I can tell, as I said, that it's somewhere here, but it may be here, maybe here, maybe closer to this point. So to do this, we can get data from all these tie lines, and use this data to get the plait point. So what we will end up with, we'll have two liquid layers. One of them is rich in B, and one of them is rich in A, which we call the extract and raffinate. And we will have C, which is this solute here, some C in here, and we'll have some C in here. And so what I'm gonna do is I got it from, it's good to share with you this textbook as well. So this textbook is a very nice textbook that is totally devoted to the liquid extraction processes, or the liquid extraction in general, by Robert Trevel. So this is a very good book. I just knew about it like soon. So he's starting with the first chapter about the liquid equilibrium, and he's like giving a very good discussion about this. So it's going to be helpful in case you want to get more information and know more details about the equilibrium and the plate point and all these things. But the point that I want to highlight here is the way he can predict the plate point. So he uses this graph, which I copied here. So he said that we can plot the XCB, which is the composition of C in the B reach phase, which is gonna be this side of the tie line, versus the XCA, which is the composition of C in the A reach phase, which is in this side. So I'm gonna plot the composition of C here versus the composition of C here, and this will produce a line that looks like this, which will end somewhere here, and we can, by extrapolation, know that this is gonna end here. So this is what we're gonna do now in using Aspen Plus. So I'm gonna use one of the examples that we used in the textbook, a mixture of water, benzene, and dioxane. So water is A, benzene is B, and dioxane is C. Dioxane is the solute, and I used the model to be, or the method to be, an RTL, and this is something I'm gonna come back to in a few minutes, but this is just something to keep in mind that I use in RTL. And then we will go to analysis. I just want to produce the experimental data. So what I'm gonna do is either go here for ternary diagram or add new here, and then I want to continue to Aspen Plus ternary diagram. The component one, which is A, is water, then B is benzene, C is the accent. So now it's okay. The experiment, or the data that I have or I know, are about 1 atmosphere, so this is right. I can get as many points as I want, up to 25, so I'm gonna put the maximum value. And then I want it to be liquid because this is liquid process, and the temperature is 25. So I'm gonna run analysis. It's gonna produce the ternary diagram with the tie lines, and then we will get the data from here. And as you see, this is very close to what we saw before. These are all the tie lines that I have, and then I have the plate point is lying somewhere here in this region. So to do this drawings, I used Microsoft Excel. So I need to get the results. So this is the phase envelope here, which is the two phases, or the two phases together. So you'd see this is the mole fraction of water, which is the like first very low concentration and then very high concentration, and the opposite in benzene. So it's the two phases. So I will go for the equilibrium composition, because I cannot tell from the phase envelope which is XCA and which is XCB. Here, and you'd see this. I'm sorry, yeah, and here it gives me all the data that I have. So these are the data for, you can see from here, this is the mole fraction of water, this is the mole fraction of benzene, this is a mole fraction of dioxane. So this is the benzene reach phase, and this is, you can see, this is the water reach phase. I'm gonna copy this, and I'm going now to my Excel file. I have, this is the water reach phase. I'm gonna paste the values here, and then for this the 3 columns, this is the benzene reach phase, and you see this is how the curve looks like. And you can so this is what I did. I added the trend line, and then I used the trend line to do some extrapolation, but it's not gonna work, and I'll show you why. Because this is the best shot that I found was to be like third order polynomial, and if you display the equation on R square, it's perfect fit for this region. But you can do something in Excel, which is, I don't know if you're aware about it or not, or this is called forward. So instead of calculating the data for like points maybe at this region, you can ask it to like extend the graph to be maybe after point 1 or point 4, for instance. You see the graph is going this way because it's a third order polynomial, so it's not going to go like this. Maybe if you make it second order, but the second order fit is not good enough. Let's see, it's not a good fit here, so you cannot rely on this as well. So the fitting is not gonna be the option. So what I would suggest is just to extend it manually. It's gonna be not very accurate, of course, because the distance between this point and the 45 degrees line is kind of big. But you will have like good estimation of this point, which should be around 0.5 and 0.5, which is, or 0.48, 0.49, something like this. So this is how you can do this using the experimental data. Either you get experimental data from your experiments, or you get them from Aspen Plus, as I did in this video. One last thing to keep in mind is that the results will vary a lot depending on the thermodynamic model that you're using. I compared the results that I got here with the results that are in the textbook, which are these. So these are in mass fraction, and what I have is in mole fraction. You can calculate the mole fraction from mass fraction or the opposite, but the results are not like very accurate. So I know that this is not the right values compared to the other, because the other are experimental values, but this is not experimental. So what I found that this is not very accurate. So I tried many models. I tried this is the UniQuack. You see it's the same plot, but it's different values. So it's a lot of difference. I used a model called UniFac LL that is used for liquid extraction. I used one other model called SR Polar, and I used like many other models. But like this is a good example of a case where you have to find a model that fits well with your experimental data. So maybe there are other models that are more accurate that I didn't use, but these are the ones that I used. And this is something that I want you to keep in mind, that the software produces the results based on the model that you use, and the model might not be a good fit for the components that you have or the system that you have. So the choice of the model is very important and very critical. So in case you want to do this, you need to verify the model first and make sure that the data from Aspen Plus match the data from the experiment or the experimental data that you have. So this is all for this video. Hope it helps, and I'll see you in the next video, inshallah. Goodbye.